Ever notice how some spices, like, they vanish when you add them to a recipe,
Right.
and others, they just clump together no matter how much you stir?
Yeah,
It's, like, easy to overlook those little quirks of powders, but
it's true.
believe it or not, the way these tiny particles behave, it's actually, like, surprisingly complex,
Oh, absolutely.
especially when it comes to pharmaceuticals.
It's true, and that's because even though we rarely think about it,
Yeah.
the science of small particles, we call this micromeritics, it plays a huge role in how medicine actually works in our bodies.
Micromeritics.
Yeah.
Okay, I'm already intrigued.
Okay, good.
So we're talking about, like, more than just the ingredients themselves. It's
Yeah.
the size
It's the size.
and shape of these, like, tiny particles that can make or break a medication.
Exactly. To give you one example from what we're looking at, the speed at which a drug dissolves and then gets absorbed, that depends significantly on these particle characteristics.
Wow.
So just imagine a pill, right, entering your stomach. The size and the shape of those drug particles,
Yeah.
they can actually affect how quickly it breaks down and gets to work.
That's wild. I never considered that something so small could have such a big impact, you know? It's like each particle has a critical mission or something.
They do, they do.
But how do we even begin to measure something as, like, seemingly abstract as the size of a particle? Especially when most aren't, like, you know, perfect little spheres.
That's a really good question because we are dealing with irregular shapes, not tiny marbles, right?
Right.
So in micromeritics, we use this concept called equivalent sphere diameter.
Okay.
Essentially what we're doing is we're finding a sphere that would behave similarly to the particle we're analyzing.
Interesting.
It lets us make comparisons and it lets us make predictions.
So it's like finding a spherical stand-in for
Yeah.
those odd-shaped particles.
Exactly.
Clever, but I imagine it can't be that simple, right?
Yeah.
What about, say, a long, thin particle compared to a more compact one? They might have the same, like, equivalent sphere diameter, but look and act completely different.
You're absolutely right. And that's where aspect ratio comes into play.
Okay.
So we look at the ratio of the longest dimension of the particle to its shortest. And this helps us, for example, distinguish between a needle-like particle and a more rounded one, even if they have the same equivalent sphere diameter.
I'm starting to see how scientists are, like, building a whole system to categorize and understand these particles, you know?
Absolutely.
It's like a secret language.
Yeah,
We're describing the, like, building blocks of powders.
It's true.
But this seems incredibly detailed.
It is. It is.
Are we talking, like, electron microscopes and lasers to measure these things?
Well, we do have some high-tech methods,
Yeah.
but some are surprisingly simple.
Okay.
Our source material actually lists sieving as one technique.
Sieving, like the thing my grandmother uses for flour.
Dressing.
That's how we're analyzing these tiny particles.
For some applications, absolutely. So sieving involves passing the powder through a series of sieves.
Okay.
And these sieves have progressively smaller and smaller holes.
Okay.
And it's a really straightforward way to just get a sense of the particle size distribution within a sample.
Okay, so sometimes the old ways are still the best.
Sometimes the simplest way is the best way.
I like it. I like it.
Yeah.
But what about those high-tech methods you mentioned? Like, what can we learn by getting even more precise with our measurements?
Well, laser diffraction is one technique that offers incredible precision.
Okay.
Imagine like shining a laser beam through a cloud of these particles.
Right.
The way the light scatters.
Yeah.
That depends on the size of those particles.
Interesting.
So by analyzing the pattern of this scattered light, we get a really accurate picture of the particle size distribution in the sample.
So we're basically shining a light on the secrets hidden within these powders.
Exactly.
I'd never considered how much information we could get from something so simple.
Yeah, it's really fascinating.
Yeah. But why go through all this trouble? You know, what's the practical application of being able to, like, analyze particle size so precisely?
Well, it's all about controlling consistency, especially in pharmaceuticals.
Right.
Imagine you're creating a medication where the dosage is critical.
Right.
Even tiny variations in that particle size distribution.
Yeah.
That could lead to significant differences in how the drug is absorbed.
Makes sense.
And ultimately its effectiveness.
So you want every pill, every capsule to behave predictably in the body.
Yes,
Be
absolutely.
delivering that same dose every time.
Dose of accuracy is key.
Exactly. Exactly.
Yeah.
But it's not just about medicine, is it?
It's not, you're right.
It goes beyond that.
Micromeritics is vital in many industries.
Yeah, I bet.
From, making sure your cosmetics have a smooth texture to even, like, controlling how ingredients interact in food science.
It's amazing how these tiny particles, things we rarely even think about, can have such a huge impact on the world around us.
Right. It really is fascinating.
Speaking of hidden complexities,
Okay.
our source material, it goes on to mention something called particle surface area. Now, why would the surface area of a powder be so important? It's not like we're painting it.
You'd be surprised. The surface area of a powder. It's crucial because it directly affects how fast it dissolves. Think about it this way. When you crush a pill,
Yeah.
it allows your body to interact with more of the drug's surface area, making it work faster.
Oh, interesting.
The same principle applies to powders in general.
That makes sense, yeah.
Yeah.
So the more surface area that's exposed,
Yeah.
the more contact points for, like, the solvent to work its magic, so to speak.
Exactly.
So a powder with a larger surface area.
It's going to dissolve much faster in general.
Interesting.
Yeah.
Okay, so we've got particle size,
Yes.
shape, distribution, and now surface area. It feels like we're building like a toolkit
We are.
to decode these powders.
That's a good way to put it.
I like it. But our source material doesn't stop there, though.
It does.
It delves into powder density and volume,
Okay.
even mentioning different types of density.
Yes, it does. And this is important.
I have a feeling this is about more than just how much a powder weighs.
You are absolutely right.
Okay.
So the source material kind of introduces us to these terms like
Yeah.
true density,
Okay.
bulk density, and tapped bulk density. And while it seems like, oh, this is a bit excessive,
Right.
these variations tell us very different things about how the powder behaves.
Okay, I'm ready for a crash course on powder density.
All right, let's do it.
What makes these densities so special, and why should we, care about the differences between them?
It's all about understanding how those tiny particles interact with each other.
Okay.
So let's start with true density.
Okay.
This is essentially the density of the material itself.
Okay.
We're ignoring any space between those particles.
Okay.
Imagine like a perfectly packed solid chunk
Okay.
of that material.
Got it.
That's its true density.
So the true density is like the baseline. But in reality,
Yeah.
powders are never perfectly packed.
They're not. You're absolutely right.
And that's where bulk density comes in, right?
Exactly. Bulk density takes those tiny spaces between the particles into account.
Okay.
And it gives us a measure of how efficiently they pack together.
Interesting.
So a powder with a low bulk density is going to be what we call fluffier. It'll take up more space.
Okay.
And a denser powder is going to be much more compact.
So, a bag of marshmallows
Yes.
would have a much lower bulk density than a bag of sand, even if they weighed the same.
You got it.
It's like comparing a pile of, fluffy cotton balls to a bag of marbles.
I love the way you think.
Right.
So very different.
Yes.
Okay.
Now, imagine you have a container of that powder.
Okay.
Tapped bulk density is measuring how that density changes
Okay.
when you tap or vibrate the container, allowing the particles to settle more tightly.
So we're giving those particles a little encouragement to find their happy, tightly packed place.
Exactly. Get in there and get settled. I love it. It seems like these different densities would have, real-world implications,
They absolutely do.
especially when you think about packaging and shipping.
Absolutely. A powder with a low bulk density might require a much larger container than a denser powder, even if they weigh the same. And this can affect cost, this can affect storage, it even affects how they're handled during transport.
Makes a lot of sense.
Yeah, absolutely.
And I imagine these, density variations could also impact the design of, manufacturing equipment.
Oh, absolutely.
Like how easily a powder flows through a chute or, fills a capsule.
You are spot on. And that brings us to another crucial aspect of micromeritics, powder flowability.
Flowability. Now, that's a concept I can get behind.
I thought you might like that one.
I do.
Yeah.
Because, some things flow like a dream, others not so much.
Exactly.
It's like trying to get ketchup out of a glass bottle,
Oh, the worst.
Some days it's a smooth operation, other days, forget about it.
The perfect analogy, though, because just like with ketchup, some powders are naturally stubborn
Right.
and they tend to clump together,
Yeah.
while others flow very freely.
Right.
And in pharmaceuticals,
Yeah.
these differences can have significant consequences.
I bet. Especially when we're talking about potentially life-saving medications.
Absolutely.
Any hiccups in flowability
Yeah,
could throw things off in a big way.
they can.
Yeah, tell me more about how flowability affects that, manufacturing process.
Well, think about the different stages of drug production, right?
Yeah.
You have to blend the powders for a uniform mixture.
Right.
You have to fill capsules with those precise doses.
Right.
And even compressing powders into tablets, all of these rely on good powder flow.
If a powder isn't cooperating, you could end up with, like, uneven mixtures, inconsistent doses in the capsules,
Exactly.
or tablets that crumble too easily.
Absolutely.
That's not good.
Not good.
Not good at all.
No.
So understanding and controlling powder flowability
Is this
for ensuring, like, the quality and consistency of pharmaceutical products.
100%.
Okay, so how do scientists even begin to measure something as, like, seemingly abstract as flowability?
It's a good question.
Do they gather around a funnel and just, see how fast it pours?
You're not far off.
Am I not?
No, you're not.
Okay.
The source material describes a method called the angle of repose.
Angle of repose.
Yes.
It sounds almost poetic for something as practical as measuring powder.
It does. It does. But it's actually a very simple yet insightful test.
Okay. What exactly does it mean?
So it's all about how steep a pile of powder can get before it starts to collapse.
Interesting.
You let the powder flow freely onto a surface, and it creates this little cone-like pile.
Right.
The steeper the angle of that cone,
Yeah.
the less flowable the powder is.
So a powder that forms a tall, pointy pile.
It's like your ketchup bottle. Very stubborn.
There we go. Not very cooperative.
Exactly. A steeper angle means that there's higher friction between the particles, making them more resistant to flow, whereas, a powder that forms a flatter pile,
Right.
that's your free-flowing guy.
I like it. So this angle of repose gives scientists, like, a visual and measurable way
It does, yep.
to assess flowability.
The simple visual.
What a clever way to quantify something that seems so abstract.
Isn't it? Yeah.
Are there other techniques used to measure flowability?
There are.
Okay.
Another one mentioned in the source material is what's called the Hopper flow rate.
Hopper flow rate definitely sounds more technical than angle of repose.
It does, doesn't it?
It does.
It does.
Tell me more.
Picture a hopper, like a large funnel
Okay.
filled with powder.
Yeah.
The Hopper flow rate measures how quickly that powder empties from that container.
Okay.
It's a direct measurement of how freely that powder flows under gravity.
So a high Hopper flow rate means the powder is practically flying out of the container,
Pretty much, yeah.
and a low flow rate means it's, dragging its feet a little bit.
Yep. Exactly. And these measurements, along with the other factors we've talked about,
Right.
really help these companies ensure consistency and predictability in their processes.
It's incredible to think about all the science and engineering that goes into something as, like, seemingly simple as creating a pill
Yeah.
or filling a capsule.
It is. It's amazing, isn't it?
It is. We've uncovered a lot about these particles.
We have.
But I have a feeling our Micromeritics journey isn't over yet, is it?
Oh, no, we're just getting started.
Okay. What else can you tell us about this hidden world that influences so much of what we see and use every day?
Well, let's dive a little deeper into the world of tablet manufacturing,
Right.
because it's quite fascinating how those particles behave under pressure.
It really makes you think twice about those innocent-looking pills in your medicine cabinet.
It really does.
We've already uncovered so much about these powders, but our source material mentions something called the Compressibility Index
Okay.
and the Hausner ratio.
Right.
Those sound a bit intimidating, even for this deep dive.
They do sound a bit technical,
Yeah.
but they're really essential for understanding how powders behave under pressure,
Okay.
especially in something like tablet manufacturing.
Okay, you've piqued my curiosity. Let's start with Compressibility Index. What's the deal with that? Is it like measuring how squishy a powder is?
You're on the right track. The
Yeah.
compressibility index basically measures how much a powder's volume changes when you apply pressure to it.
Okay.
So remember tapped bulk density?
Yeah.
Well, this index, we calculate it using the difference between the powder's initial bulk density and its tapped bulk density.
So it's like comparing how much space a powder takes up
Yeah.
before and after giving it a good shake.
Essentially, yeah.
I imagine a bag of feathers would have a much higher compressibility index than, say, a bag of marbles.
Precisely.
Right.
And this property, this is really important when we're talking about making tablets.
Okay.
Because powders with a high compressibility index, they tend to be a little less cooperative during manufacturing.
Oh, really?
Yeah, they might need higher pressure to form those compact, nice, uniform tablets that, we rely on.
That makes sense.
Yeah.
You'd need a lot more force to, like, compress a pile of feathers into a solid tablet than you would, say, sugar. Right?
Exactly. That's a good way to think about it.
The compressibility index helps predict how a powder will act during that whole tablet making process.
That's right.
What about the Hausner ratio?
Okay.
How does that fit into all of this?
So the Hausner ratio is another way to kind of assess powder flowability
Okay.
using those same density measurements.
Okay.
We're talking bulk density and tapped bulk density.
Right.
You simply take the tapped bulk density, divide it by that untapped bulk density, and that gives you your Hausner ratio.
So it's another way of looking at how much the density changes under pressure.
Yeah, pretty much.
But this time we're doing a bit of math
A little bit of math.
to get a specific ratio.
Yep.
What's the significance of that number in the pharmaceutical world?
So a higher Hausner ratio. That generally points to poorer flowability.
Okay.
Think of it this way. If you have a big difference between those untapped and tapped densities,
Yeah.
that means the powder has a lot of air spaces that can be compressed.
Right.
And that can lead to things like uneven filling or tablets that don't quite form properly.
So for smooth sailing, basically in that manufacturing process, you want a powder with a lower Hausner ratio,
You got it.
suggesting it flows more easily and predictably.
Exactly.
Got it.
It's all about making sure those medications are produced consistently, reliably.
Right, right. Very important.
Yep.
It's like we're building a whole vocabulary to describe the personalities of these powders, you know?
I like that. It is like giving them a personality, isn't it?
Right. They're very complex.
They are.
But our Micromeritics journey, it isn't over yet, is it?
It's not over yet. We've got a lot more to uncover.
The source material, it hints at even more factors influencing these tiny particles.
It does.
What else can we add to our toolkit?
Well, we've covered a lot of ground, but there's one more important factor to consider,
Okay.
and that's porosity.
Porosity. Now we're getting into, the nooks and crannies of these powders.
We're going even deeper.
It sounds like we're going even deeper into, the micro world.
Exactly.
What exactly is porosity when we're talking about powders?
So think of a powder bed, right? Like a collection of those tiny particles
Okay.
with spaces in between them.
Yeah.
Those spaces, or voids we call them, those contribute to the powder's overall porosity.
Okay.
It's essentially a measure of how much empty space exists within a given volume of powder.
So a powder with high porosity would have a lot of gaps between its particles, kind of like a sponge.
Yes, like a sponge.
While a powder with low porosity would be more tightly packed, like sand almost.
That's a great analogy.
Right.
Yeah.
So very different.
Very different.
I can see where this is going.
Okay.
It's about more than just how much water a powder can soak up, right?
Right. It goes beyond that.
How does porosity affect those tiny drug particles on their mission to deliver medication?
So porosity can affect things like, for instance, how quickly the powder dissolves.
Okay.
More porous powders often dissolve faster
Okay.
because the solvent has more channels to penetrate, to interact with all those particles.
So it's like having more surface area exposed for the solvent to, work its magic.
Exactly.
Even if the particles themselves aren't necessarily larger.
That's right.
Got it.
And remember our earlier conversation about how that dissolution rate is so crucial for drug absorption.
Right, right.
So by controlling the porosity, scientists have another tool to fine-tune how effective that medication is going to be.
It's amazing how interconnected all of these factors are.
It really is.
From particle size and shape to surface area, density, flowability.
Yep.
And now porosity.
It's all connected.
It's like a delicate balancing act to ensure that a medication is both effective but also easy to produce reliably.
Absolutely. A very delicate dance.
Right.
Yeah.
So
Very complex.
I'm all ears for what other fascinating calculations methods do they use to get these powders to cooperate?
Well, one interesting concept is bulkiness. And it might sound familiar
Okay.
because it's essentially the opposite of bulk density.
Okay, yeah, I remember our marshmallow versus sand analogy.
There you go.
A fluffy powder has low bulk density,
Low bulk density.
while a dense powder has high bulk density. And
Yeah.
we're flipping the script now?
They're flipping it.
Okay.
So bulkiness tells us how much space a given weight of powder takes up.
Got it. Okay.
A bulky powder has a high bulk volume, while a very dense powder has a low bulk volume. Same idea, just we're looking at it from the opposite perspective.
So instead of asking, how much does this volume of powder weigh?
Yeah.
We're asking how much space does this weight of powder take up?
You got it.
It's like a game of powder Tetris.
I love that. I've never heard that before, but it's very fitting.
Right. How do we fit these in the most efficient way possible?
Exactly. And just like in Tetris, right? Efficient packing. That's important.
Especially in pharmaceuticals.
Especially in pharmaceuticals. That's right.
It's not hard to see why a highly bulky powder would require, larger containers for storage, for shipping, which, I mean, that adds up really quickly.
Oh, yeah. Costs, logistics. It's a big deal.
Well, when we're talking about, producing these on a large scale,
Absolutely.
so it's very important.
It is.
And that's where understanding the link between particle size and bulkiness is key.
Yes,
Right.
it is.
Because generally, as particle size decreases, bulkiness increases.
That's correct.
That makes sense. Imagine those tiny particles, they just have more air spaces between them, creating a fluffier, less compact powder.
Yes.
It's like trying to fill a jar with pebbles versus trying to fill it with sand. The sand will always be more tightly packed.
Always.
Right.
Always.
Very different.
Very different. And that's a great analogy, by the way.
Thank you.
Yeah.
I try.
So pharmaceutical scientists, they have to really consider this relationship when they're developing and manufacturing these medications.
Right.
Striking that perfect balance between effectiveness and practicality.
Right. Got to make sure it works, but we also got to be able to, get it to the people who need it.
Exactly.
Right.
Yeah.
It's fascinating how something as seemingly simple as a powder can be so complex.
Isn't it? And we're not even done yet.
And speaking of complexity, we touched on, methods for analyzing particle size earlier.
We did.
Like sieving and laser diffraction.
Right.
But our source material mentions a few other techniques as well.
It does, yep.
Microscopy, for example, seems like a given. But what about the Couter Counter? That name sounds like something straight out of, a science fiction novel.
It does. It has a certain ring to it, doesn't it? But the principle is actually quite elegant.
Okay.
So a Couter counter, what it does is it measures particle size and concentration, but in a liquid.
Okay, so we're no longer dealing with just dry powders.
That's right. We're going into the liquid phase now.
Now we've got particles swimming around in fluid.
Exactly.
How do we wrangle them for analysis?
So picture a tiny hole or an aperture submerged in a conducting fluid.
Yeah.
As particles pass through this aperture, they displace a small amount of fluid, right?
Right.
And that creates a momentary change in the electrical resistance.
Interesting.
The Couter counter picks up on these changes.
Wow.
And by analyzing those changes, it can tell us the size and the number of particles that have passed through.
That's incredible.
It's a very clever method.
It's like each particle creates a tiny electrical blip as it goes through.
Yes, it's like a little signature.
And the Couter counter is there to catch them all.
That's a good way to put it.
It seems like a very precise way to measure not only particle size, but also concentration.
It is very precise. And because it counts those individual particles, it's incredibly useful when you need really accurate information about particle concentration in, maybe a liquid medication or something like that.
Makes sense. Makes sense.
Yeah.
So between microscopy, sieving, laser diffraction, and this Couter counter,
Right.
scientists have a whole arsenal of tools to analyze particle size.
They do.
Depending on the specific needs of the situation, really.
Exactly. The right tool for the job.
Right, exactly.
Yep.
But let's shift gears for a moment
Right.
and go back to surface area.
Okay.
We know it's a key player, especially for dissolution rate.
It is.
And the source material mentions a couple interesting methods for determining surface area,
Just.
gas absorption,
Okay.
and permeability. Can you shed some light on those?
Absolutely. So imagine a surface.
Yeah.
Right? And it's covered in these tiny little bumps and crevices,
Okay.
much like the surface of, one of these particles. Even if we can't see those features with the naked eye,
Right.
gas absorption takes advantage of the fact that certain gases, under specific conditions, will adhere to these surfaces.
So it's like we're using gas molecules to map out the contours of these tiny particles. That's so cool.
It's a very clever method.
I love it.
So by measuring how much of that gas is absorbed at different pressures, we can back calculate and figure out the total surface area of the material.
So the more gas gets absorbed, the larger the surface area.
The larger the surface area, that's right.
It's like measuring the surface area of a sponge by seeing how much air it can hold.
I like it. That's a great way to visualize it.
Right.
Yeah.
Okay.
Now, permeability is a bit different.
Okay.
Instead of measuring how much of that gas sticks to the surface, we're going to measure how easily a gas or a liquid flows through a packed bed of that powder.
So we're essentially measuring how much resistance the powder puts up to the flow.
That's a good way to put it, yeah.
Okay.
And that resistance, that's directly related to the surface area of those particles.
Got it.
A powder with a higher surface area is going to put up more resistance to that flow, so it's going to have a lower permeability.
It's mind-boggling how something as simple as measuring flow
Right.
can give us insights into the surface area
It's incredible.
of these tiny particles.
It is.
And it really highlights how much science goes into something as, like, routine as taking a pill.
Absolutely. We don't think about it, but it's happening.
Exactly.
All this science is happening.
A lot going on.
It is.
And it's not just pharmaceuticals that benefit from this understanding of particles, is it?
Oh, no, not at all.
It goes way beyond that.
It does.
Right? From, like, the texture of our food and cosmetics
Right.
to the performance of, like, paints and countless other materials.
Absolutely, yeah.
This hidden world of particles impacts, so many aspects of our lives.
It really does.
It really makes you appreciate the power of, like, scientific inquiry,
It does. It's amazing.
And the importance of paying attention to those tiny details that we often take for granted.
Right. They're small but mighty.
Exactly.
Yeah.
But before we get too philosophical, our deep dive into Micromeritics, it isn't over yet.
Not even close.
We've covered a lot of ground.
We have.
But something tells me there's still more to uncover about these fascinating particles and their impact on how medications work.
Oh, there's always more to learn. There's always more to explore.
It's amazing how we've journeyed all the way into the world of particles, like exploring their shapes, sizes, even how they pack together.
It's a wild ride, isn't it?
It is. But let's bring it back to what matters most,
Okay.
How do all these microscopic details, like how do they actually impact the effectiveness of a medication?
Well, that is the million-dollar question, isn't it?
It is.
Everything we've talked about, right? From particle size and shape to, porosity, flowability, all of these things ultimately influence how well a drug does its job in the body.
So it's like each pill or capsule is this like tiny, intricate machine, and those particles are like the gears and cogs.
I like that analogy. That's a good one.
Right. That make it all work.
Yep.
What happens if those parts aren't designed just right?
Well, let's say, for example, we have a drug that has poor solubility, meaning it doesn't dissolve well in the body's fluids. That can be a major, major roadblock.
Right.
Because if the drug can't dissolve properly, it won't be absorbed effectively.
That makes sense. Yeah, it's like trying to make a cake with like chunks of flour that never blend into the batter.
Yep.
You're not going to get like a very appetizing result.
No, you're not. And that's where that deep understanding of Micromeritics becomes so crucial for these scientists.
Right.
Because by controlling those particle characteristics, they can improve how well that drug dissolves.
Right.
How quickly it dissolves.
Got it.
And that ultimately affects how much of it actually reaches the bloodstream where it needs to be.
Which brings us to bioavailability, a term I've like always heard in passing.
Yes.
But like never fully understood. It's
Okay.
about how much of the drug actually gets to where it needs to be in the body
Yes.
to actually take effect, right?
100%. You got it.
Okay.
So bioavailability, think of it as like a measure of the drug's journey from that pill or capsule
Right.
all the way into your bloodstream.
Okay.
And it's influenced by many factors, but particle characteristics play a huge role here.
Makes sense.
For example, just by simply reducing particle size,
Yeah.
you increase that surface area, which can lead to faster dissolution,
Right.
faster absorption, meaning higher bioavailability.
So sometimes something as like straightforward as like grinding a drug into finer particles
Yes.
could make it more effective.
It can. It really can.
That's incredible.
It is. It highlights how, this deep understanding allows scientists to refine these drug formulations.
Yeah.
They can tweak things, make sure the medications are delivered more efficiently, maybe have fewer side effects,
Right.
maybe even taste a little bit better. You never know.
Now that's what I call a win-win-win. Who knew that these tiny particles held the key to such significant improvements in medicine?
Right. It's pretty amazing.
It really is.
Yeah.
It
Yeah.
seems like we've reached the bottom of our Micromeritics deep dive.
I guess so, yeah.
We've explored this like hidden world, uncovered its secrets,
We did.
and seen firsthand how all of these tiny wonders impact, our lives.
Absolutely. It's been a fascinating journey.
It has.
And I hope our listeners have gained a new appreciation for this intricate science, right?
Yeah.
That goes into something as, routine as just taking a pill.
Right. We don't even think about it.
We don't know. It's a world we rarely think about, and yet it's so vital to keeping us healthy.
Absolutely. So the next time you open your medicine cabinet, take a moment to think about those tiny particles working hard inside each pill and capsule.
It's like this microscopic world
It is.
of scientific ingenuity,
Yeah.
just quietly and reliably making sure that those medications can do their job.
This deep dive into Micromeritics has been really eye-opening.
It has.
And it's definitely giving me a whole new perspective on like the hidden world of medicine.
I'm glad to hear that. Me too.
Until next time.